In this video, we're looking at atomic orbitals. So, what is an orbital? An orbital is a region of space in which two electrons can occupy that have opposite spins. And spin is sort of strange concept. It's quantum mechanical. It's the intrinsic angular momentum of an electron. Now that's getting a bit deep into quantum mechanics, but that's what you need to know. So two electrons can occupy each orbital. Okay, there's four types of orbitals, or actually, that's not true. There's four types of subshells, which have different shapes and things. So there's S subshells, D subshells, P subshells, and F subshells. Okay. An example: a shape, or the shape of an S orbital is always a sphere with the atom in the middle, and the orbital is just a sort of statistical function of where the electron is likely to be. The shape of D orbitals, P orbitals, got it the wrong way around. Got it the wrong way around here. So a P orbital. No, let's just do it again. So let's just clear it. In this video, we'll be looking at atomic orbitals. So, what's an atomic orbital? Or what's an orbital at all? An orbital is a region of space in which two electrons of opposite spins can occupy. So what the spin of an electron is intrinsic angular momentum, and that's a quantum mechanical term. And don't worry about that. So two electrons can occupy an orbital, and there are four types of subshells in which orbitals are a part of. So there's S, P, D, and F. The shape of S orbitals is always a sphere with the atom in the middle, and let me just explain that this orbital is technically a statistical function, because electrons have a chance or a probability of being in that area, in that volume technically. An example of a shape of the p orbital is always actually a dumbbell shape. So it's always, imagine the atoms in the middle of this intersection point, and then the p orbital can go in three directions, so x, y, and coming out z. Now this is where I'm just going to give an example of a d orbital, because this is where it gets a bit strange. So the d orbital has like a sort of donut shape around here. Okay, it has a sort of part on top, and I'm not sure if you can imagine it, the atom's going to be in the middle here. So, so that donut's a bit thick. But yeah, so it's like a sort of thin donut around the atom with sort of pieces on top and below. Okay? And then F is even stranger. That's similar to D actually. One example similar to D has two sort of donuts around, and then it has these pieces on top. Okay, and the atoms in between these two donuts. So that's not most well drawn. The atoms in between here. Drawing that, and then it has another below. Has another part there below. So s orbitals, there's only two electrons that can occupy that space. There's three separate configurations of the p one, so 6 electrons occupy the p subshell. D has 10 electrons, and F has 14 electrons that it can harbour. Okay. Orbitals fill in terms of energy. So, for example, the principal quantum shell is the energy level of these orbitals, and there is an I'll just show by example. With the first principal quantum shell, there's only s orbitals. So there's his s, only s, and n equals 2. There is s and p. Now this is actually energy. Okay. N equals 3. There is s, p, and now n equals 4. 4s fills first, and then 3d has a higher energy level. So let me just draw lines to each of these. Has a slightly higher energy level. So actually, the 4s shell fills first. Now, let me show you by example some configurations of elements and ions and things. So, one example I can show is the electronic configuration of calcium. So that's 1s. Actually, let's just establish how many it has. So calcium has 20 electrons as a stable atom. It's not an ion. So 1s2, 2s2, 2p6. That's 10 electrons. 3s2. That's 12. 3p6. That's 18. And now it's not actually 3d2. It's 4s2 because that fills first, as it requires less energy for that to be filled. Let's do vanadium. That has 23 electrons. Okay. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 4s2 fills first again, and then 3d3. So let's just count that. That's 10, 12, 18, 20, 23. Okay, the last one, sodium ion. Sodium plus. So this has an equivalent electronic configuration to neon. So as it's lost an electron, so it's 1s2, 2s2, 2p6. Now, this first number here in front of each of these refers to the principal quantum number, so n equals 1, n equals 2, etc. And the superscript numbers here refer to the number of electrons in the subshell.